Hello, my name is Anna Boscarino and I am a doctoral candidate at NJCU. In this video, we will be discussing Anova. We will begin by defining Anova. I will share a scenario in an educational setting where this statistical test should be used. I will also demonstrate how to calculate it using SPSS software and later show you how to conduct an ad hoc test to determine where the statistically significant variance lies. Lastly, I will interpret the findings and show how the results can lead to decision-making in the educational setting. What is ANOVA? ANOVA, or analysis of variance, is an inferential statistical test measuring differences in the means of groups, testing on more than two levels of the same variable or variables. To measure variance, a researcher would use an F-test, named after the statistician who created it, R.A. Fisher. While there are numerous ANOVA tests, the scope of this video will only include a simple analysis of variance. This is when you analyze only one variable on at least two levels. When testing more than one treatment factor, a factorial design ANOVA would be used. Variance is analyzed as the ratio of differences within the groups, which represents differences in the individuals themselves, and the difference between groups, which is a result of the treatment. Is a simple ANOVA the right fit? There are a number of criteria that needs to be met before selecting an ANOVA test. Are you analyzing relationships between groups based on one or more variables? Are the same participants only being tested once, and do you have more than three groups? If you answer yes to all of these questions, then an ANOVA is the right instrument. The formula for a one-way ANOVA is quite simple. The mean square between represents the variance between the groups, while the mean square within represents the variance within the groups. This is a ratio. So if the ratio is 1, the variability between groups is equal to that within groups and is therefore not significant. Increased levels of variability between groups leads to a greater number and in turn a greater F value. Extreme F values, therefore, are more likely to be statistically significant for reasons other than chance, such as the effects of the treatment. Let's take a look at a fictional study I created for this video. A Title I school decided to create an after-school program to help students prepare for the PARCC testing. The school district wants to know if the length of the program makes a difference. This is important because you want a program that is effective, but you don't want to waste more funds than necessary. So in this case, they create 3 treatment groups that are randomly assigned. The first group is in the program for 3 months, the second group participates for 6, and the last group participates for 9. The school receives the test scores for the participants during the summer months and decide to conduct a one-way ANOVA test to see if there are differences between the groups. Following proper research protocol, the administrators begin by stating the ho and the ha. In this case, the ho, or the null hypothesis, states that there is no difference between the 3 groups, while the ha, or alternative hypothesis, states that there is a difference. The alpha level is set at 0.05. Now the administrators are ready to run the F-test. After the calculations are complete, they will refer to the appropriate table to determine the critical value for rejecting the null hypothesis. Once all the data is gathered, they are ready to make their decision. To calculate the different sums of squares by hand, you would use the following formulas. While it seems complicated, it really is just basic arithmetic. Although, let me tell you, it is tedious and very time-consuming. For the purposes of this tutorial, I won't go into specifics how to calculate them by hand, but will instead show you how to calculate them using SPSS software. We begin by inputting the length of the program and the PARCC scores for all participants. I inputted them earlier to save time. We are now ready to run a one-way ANOVA test. Go to the Analyze tab, then go to Compare Means and select One-Way ANOVA. A pop-up screen will appear. Select your dependent variable or the variable that we suspect is under the influence, in this case, the PARCC scores. Click the arrow to move it to the right. Next, select your factor or length of program and click on the arrow. On the right-hand side, select Option and check off the descriptive box. Continue and select OK. Your descriptive statistics provides you with general information including mean and standard deviation for the 3 groups. Under the ANOVA, you will see the sum of squares, the degree of freedom, and mean of squares between and within groups. The program automatically gives you the F score and determines the level of significance for you, saving you time. As you can see, an F score of 5.292 is statistically significant at our alpha level, which we set at 0.05. While this information tells us that there is a difference between the groups, it doesn't tell us which groups. Are all three significantly different or just one or two groups? To determine this, we will now run an ad hoc test. This test is only relevant if you've established statistical significance between the groups. Go back to the Analyze tab and select Compare Means. This time you will click on Ad hoc on the right-hand side. Select REGWQ and Tukey. There are different types of ad hoc tests that you can use depending on your data set. Since we have equal variance and equal n size for all groups, we can either go with the Tukey honestly statistical difference or REGWQ. We will select both of these and run our test. Now we are ready to analyze the difference between the groups. In the first table, you see each group being compared to the other groups. In the first section, you see the 3-month group in comparison to the 2 other groups. Both have an asterisk next to the mean difference indicating a statistical difference. In other words, there is a difference between those who only had the intervention for 3 months in comparison to those who had it for 6 or 9 months. And we can also determine that the chances of this difference occurring by chance is only 5%. We next look at the other 2 groups and we can determine that the difference between the 6-month and the 9-month group is not statistically significant. With a value of 0.755, we cannot reject the null hypothesis at the 0.05 alpha level. In the second chart, they show the homogeneous subgroups. So the mean for the 3-month group is statistically lower than the other 2 groups, which are categorized together. We are now ready to report our findings. In summation, there was a significant difference between the scores of the students enrolled in the 3-month program in comparison to those enrolled in the 6 and 9-month programs. We could not, however, reject the null hypothesis stating that the means of the 6 and 9-month programs were equal. Based on the findings of the Anova, the school district decided to create a 6-month intervention program for the following year for all students. They figured that 3 months was not long enough to produce a statistically significant improvement in PARCC scores. They do see a significant increase in 6 months, but not between the 6 and 9 months program. While this was the decision the district made, they could have opted to run another study to look at the 6 and 9-month programs again. While not statistically significant at the 0.05 alpha level, it was close at the 0.07. The results are never definitive since you always run the chance of having a type 2 error where you fail to reject the null hypothesis and there is a difference between the groups. I hope this video has taken the detective work out of calculating Anova and you have a better understanding of how and when to use it.